Welcome to this session of fluid inclusions in minerals. In this module, we will be discussing about the principles of microthermometry, and in the last class we discussed about certain specifications, requirements that these heating freezing systems must meet, must qualify for carrying out the microthermometric experiments on these fluid inclusions. We discussed about their certain specification in terms of their range of operation, the thermal response, ease of operation, changing from freezing to heating mode, and many of the other aspects which we discussed in the last class. We will quickly have a view of these microthermometric apparatus, or which are the microscopic heating freezing systems which are mounted on microscopes. There are many such commercially available models which you will find in any of the research laboratories carrying out fluid inclusion work anywhere, and without getting into too much of the minor details about this equipment which one can experience when one starts working with them. So, this one which is here in this figure, this picture, it's this is a heating gas flow heating cum freezing system, originally designed by the United States Geological Survey and is adopted by the Fluid Incorporated in Denver, Colorado, United States of America. And the basic operation of this heating freezing system is that the freezing is done by cold nitrogen gas. The nitrogen gas is it comes from a commercially available nitrogen gas cylinder, and this, which is the container of liquid nitrogen, the liquid nitrogen dewar, within that there is a copper coil assembly, and the dry nitrogen gas is made to circulate through this assembly and is controlled by the flow meter over here, which makes the nitrogen gas flow at a specific rate, and by which the gas nitrogen gas gets cooled, and you can see a well insulated delivery tube which is connected to the heating freezing system, which is a ceramic stage, and within which the sample holder, the chamber is placed. Within that chamber, the fluid inclusion, the wafer, the doubly polished thin section in which we study the fluid inclusions is kept, and the heating is done. So, within this there is a heating element, and the heating is done by passing compressed air, and by applying desired current, the heating element gets heated up, and the sample chamber gets heated, and the temperature is recorded by this device, which is a temperature indicator, or it is a trend indicator. And so, this system, the way it works, that the attachment for heating and freezing are different. So, once the freezing is done, or freezing work is completed, then the this cold nitrogen gas delivery tube is detached, and the hot compressed air tube is attached to it, and the heating is done, and the temperature is temperature of any phase change, as we see through the microscope, or if this microscope is fitted with a digital camera and on a computer screen or on a display video display unit, we can record the phase changes and record the temperature from reading out from the value here. And these systems need to be calibrated with available standards. The synthetic fluid inclusion standards these days are available, which can be a pure water or a pure carbon dioxide, or inclusions trapped at any different pressure temperature conditions, or even there are certain other type of metallic standards with known melting point which can also be used to calibrate this equipment, and this kind of periodic calibration is essential to record the fluid inclusion thermometric observations. So, this is essentially known as the gas flow heating configuring system, and this popularly known as the Reynolds stage, named on the by the person who has fabricated this equipment. The other one which is also quite popular is the Lincoln THMS G600 microscope, heating the hot and cold stage. So, this particular Reynolds stage, it works in a range of minus 196 degrees Celsius, that is the temperature at which nitrogen boils at atmospheric pressure. So, about 196 degree centigrade or minus 76 Kelvin. So, this and the depending on the specific the capacity of this heating element, by applying the current through this variable transformer, the temperature range of operation can go to minus 196 to plus 700 degrees Celsius, and there are devices which can be used to avoid the condensation of moisture when the stage is cooled to sub-zero temperatures, as well as to also protect the objective when the temperature goes above 500 degrees Celsius temperature. So, this particular stage also works more or less in a similar manner, but the only difference is that it does not need to be the freezing and heating modes does not need to be any changeover or connection or disconnection of the tube, and here we can see the system in its totality. So, this is a temperature controller, this is the liquid nitrogen pump, and this liquid nitrogen pump pumps the liquid nitrogen from this dewar at any controlled rate as we desire, depending on the rate at which we would like to decrease the temperature or freezing or during, and this system here it actually the heating is done by applying the by the temperature controller by setting the limits of heating and also the heating rate, and this is the silver heating block on which the sample holder, as you can see, is roughly about even less than about 2 centimeter in diameter and having a central aperture for central hole for the light to pass through when it is mounted on a transmitted light microscope. And this system also needs to be in its the configuration in which the model in which it is shown here. It also needs to be the device for the anti-frosting, that means the avoidance of condensation of moisture on the glass windows or on the objective, which will obstruct the optical path for which the nitrogen gas is allowed to flow in the form of a jet, so that it drives off the moisture. And the temperature when it goes above 300 degrees Celsius, it can be, there will be water circulation system which can be designed, or even sometimes there are better available device from the manufacturer which will do the water circulation. And so here we can make a guess that the size of the wafer on which we could do the microthermometric experiment would be limited, although the initially when we carry out the fluid inclusion study under a normal microscope, we can use a larger size wafer or the doubly polished thin section that we discussed, and while bringing it to the stage, hot and cold stage for taking the microthermometric run, they need to be broken down to smaller pieces, smaller sizes, as we will see them later on. So, there are other models of this heating phasing system, and these days there are many other such makes which are of multi-purpose uses, like for material scientists and for biological purpose, and the stages that are used for the microthermometric experiments for fluid inclusions are the ones which we just briefly discussed here. So there are these kind of systems here. The as you can see here, the sample chamber here can be moved in the x and y direction from the knobs which are shown here as 1 and 3. This sample chamber can be opened for inserting the sample chamber or taking it out, and this is connected to a platinum resistor which reads the temperature. And the advantage of this particular Lincoln stage is that the temperature at any point of time can be held by the controller at that exactly at that value, whether it's depending irrespective of whether it is below 0 or above 0. And these kind of stages are also can be calibrated by using synthetic fluid inclusion standards or any other standard material whose melting points are known, and it works on a 3-point calibration below 0 degrees Celsius at 0 degree or any temperature higher. So generally this kind of calibration are stored in the temperature in the controller, and they can be periodically checked or can be reset to ensure that whatever data we are obtaining from these stages are correct and also reproducible. So with this much of little bit of idea on the instrumentation, there are other makes like IceMeca, which is a French heating converging system that is also used in many of the research laboratories. And so with this and the basic idea about the functioning of this equipment and the specifications and what are the features that we should look for while going for such kind of stage heating freezing system is as we discussed before. Well, with this a brief introduction, we will now get into the proper topic of the fluid inclusion, the microthermometry, the basic principles of microthermometry. And let us first begin with the simple cases, because as we discussed there could be many questions, many uncertainties, many questions, and many of the areas in which the fluid inclusion research is actually progressing. But for a beginner we can always start with this and going by the very simple cases and the assumptions, the very basic assumptions that we made before getting into the topic of about the fluid inclusions, and before going for any further study of these fluid inclusions, we have to first consider these very simple assumptions. And if you recall, the number one assumption is that the entrapment is homogeneous, means the time at the condition during which the fluid is encapsulated in the solid lattice of the host mineral, the fluid was homogeneous, and then the fluid once trapped behaves as a closed system without any subtraction or addition of material from with the surrounding, that means with the host mineral or anything in the surrounding, and also it has followed a constant composition, constant density path during its further evolution after the entrapment of this fluid in the host mineral. And then the other assumption is that we are actually that is basically the way we are defining our problem, that we are actually sampling the fluid depending on exactly the way we are addressing the problem, whether we are trying to study an ore deposit or a metamorphic rock, and we think that the fluid that we are sampling is actually representative of the geological condition in which that prevailed during the formation of this mineral. Well, so we will go by the very simple cases. So this one is an aqueous biphase inclusion, which we have already described. These are the most common type of inclusions that we find in minerals, host minerals like quartz and all other host minerals that we discussed, calcite, fluorite, apatite, metamorphic minerals like garnet, cordierite, or even ore minerals like cassiterite, wolframite, sphalerite, and so on. So, this is a inclusion which is an aqueous biphase inclusion, where there is a vapor bubble and a aqueous liquid, and its boundary is quite distinct with respect to the solid host mineral. So, this is the liquid solid interface and this is the liquid vapor interface, and so these are the most common type, the simplest type, where we know that it's water, and this water, the only thing which we could possibly accommodate right now is that this water is not a pure water, it has some dissolved electrolytes in it. The other type of inclusions which also are very common are the aqueous polyphase inclusion, in the sense that they have liquid plus vapor plus a solid host mineral which is inside it, and as per our assumption this host mineral precipitated after the fluid was encapsulated in the host mineral, and this crystal precipitated out of this liquid when it attained its saturation concentration. So, we call them the aqueous polyphase, liquid plus vapor plus crystal, and the third most common type of inclusions are the mixed water and gas or water and carbon dioxide inclusion, where we have a liquid rich, this is a liquid aqueous liquid, this is the carbonic liquid, and this is the carbon dioxide vapor, where we see that the meniscus, the interface between the vapor carbon dioxide and the liquid carbon dioxide is not that very dark, it is rather pretty sharp and prominent. So, these are the inclusions which are very easy to identify when we see them in the inclusion in the host minerals that we are studying. So, we will try to understand the principles of microthermometry by asking this, or by trying to understand that how this possibly could have happened. Means, what are the conditions in which we can expect the fluid, the crustal fluid, the fluid that is anywhere in the subsurface could have been in what kind of a state, so that the mineral that will grow from it and will encapsulate the fluid. So, here this is a familiar, so we can attempt to understand the situation in which fluid inclusions could be entrapped and in what condition. So, as we see here, this is the unary water system. Initially we could think of it as a pure water on the pressure temperature diagram. Here this line is the with a negative slope, as we know that water increases in its volume as it decreases in volume as it solidifies. So, there is a negative dP by dt slope, and this is the solid liquid or the melting line, and this is the solid and vapor, this is the sublimation curve, and this is the curve on which there is coexistence of liquid and vapor. So, if we look at this situation, there is a huge field in which the water is stable as a one phase liquid. So, if we imagine that the condition in the crust anywhere below the surface could be, even though we have not put the exact values of the pressure, but we know that there is a vast stability field of liquid water which is capable of existence in the liquid form and can also deposit minerals depending on when the particular mineral is attaining saturation with respect to in the liquid. This is the field of vapor. So, the only condition which will give rise to a inhomogeneous or heterogeneous condition is the locus of this curve, which we call as the boiling curve, where the liquid and vapor would coexist. So, let us try to first see the well. So, the fact is that within this vast liquid field, or also for example in the vapor field, anywhere, any point on this curve will represent a certain percentage or certain volume percent of liquid and vapor, and will uniquely define a value of density of that particular fluid. And this fluid in this region where it is homogeneous liquid, and there will be points on this PT field which will be corresponding to the densities, exactly the similar density values, and we can join them with line. So, these lines actually are representing the values of a constant density. Let us say this could be a value of say 0.9, it could be a value of say 0.9, this could be a value corresponding to possibly let us say 0.85, or this is 0.7, just for the sake of value I am just putting here. So, that means these diagram, these lines which are plotted here, they represent same value of density, and that density will be also the same where the bulk density that is calculated on the basis of the ratio of the liquid plus vapor. So, as we move along this particular line, the density will be less and less, and what we observe here is that the slope of this isodensity line will also become shallower as and when the density values will keep on decreasing. Now, so this from pure water, let us move on to a water which will contain some dissolved sodium chloride in it, and we will be moving from a pure water to a system where it is just water plus NaCl. And the reason why we are considering NaCl, let me tell you it at the beginning, that sodium is the most common or most abundant of the cationic species that we see in natural encrustal fluid, and chloride is also the dominant amongst the anions, and the crustal fluid, the aqueous fluid which actually we encounter in most of the environments will have sodium chloride as its dominant species, and it has been the system which has been very extensively and widely studied as far as jet volumetric properties are concerned, and we still represent the crustal fluid as a fluid with belonging to the water NaCl system. So, let us say that this dotted lines represent a value, say let us say 5 weight percent NaCl in that particular liquid. So, then by virtue of the concentration of the electrolyte, its density will be little higher. So, the isochore will become steeper as in when we go from pure water, which is represented by this green line, to the dotted line which are, and still if we dissolve more of sodium chloride in it, let us say this is 10% sodium chloride, then the density will be still be higher, and the slope of these isochores will become steeper. So, this is a general rule. So, in the context of the fluid inclusions, this understanding will play an important role, because we will be considering the inclusion fluid to have been entrapped in the one phase liquid field, and we will be having some dissolved constituent which can be expressed in terms of the weight percent NaCl, and the isochore, the density line, because the inclusion is going to evolve, or when the pressure and temperature changes, the inclusion is going to follow this isodensity line, because of a basic assumption that we have already made. And as we all know, this is the critical point of pure water at 374 degrees Celsius and 218 bars corresponding to that. So, this is 300 and this correspond to 374 degrees Celsius and 218 bars pressure, and this 0.32 grams per cc. I mean, we express density in unit of grams per cc, and this is the critical density, that is the 0.32 grams per cc, and this is the critical isochore. This is the critical isochore. So, the situation that we consider that the fluid could have been entrapped by the growing crystal could be anywhere here, could be a situation corresponding with supercritical state, or could be similarly when we have a vapor situation corresponding to the aqueous liquid is actually in a much lower pressure but high temperature situation. There are such situations possible in the subsurface conditions, and then still it can be entrapped by a growing crystal by some mechanism, and the vapor could be entrapped. Similarly, the vapor will also have in the vapor field, it is also possible to have such kind of the lines of isodensity lines which will be intersecting the boiling curve at different pressure temperature conditions, which will see them later. The similar diagram can be explained on the basis of the what we know as from the fundamentals, the PV isotherm, and these are the different pressure, and this is the critical temperature of water, and this dotted curve here represents the situation in which there will be coexistence. There will be coexistence of liquid plus vapor, and this region will correspond to a supercritical fluid, and as we all know that within this the pressure which is below that, if we increase the pressure, then the vapor will be liquefied, and it is not possible to further decrease the volume in the after we cross this boundary where it is defined by liquid plus vapor field separating from a one phase supercritical fluid. So, this is the previous diagram, which was a pressure temperature translation of this kind of a PV or the temperature pressure diagram, in which we can this same situation could be understood in the situation which we discussed, the boiling curve, and this is the critical point of water, and this even though this is not exactly a temperature composition diagram, but here the situation is shown that from a pure vapor which to a pure liquid, or anywhere in between where it could be a mixture of liquid plus vapor, as we move towards the right, this will be the vapor will be smaller in proportion, and here it is a largely a vapor with a negligible proportion of liquid, and this roughly this dotted line will separate the two regions where it will be corresponding to the boiling curve that we showed on a pressure temperature space in the first diagram. And here the situation is that if we originally think that this inclusion was trapped over here, as the temperature will decrease, the phase separation that we see inside the inclusion will be resulting in a dominantly an aqueous liquid plus a vapor, or if the inclusion is trapped here and the temperature is decreased, then we will have a dominantly a liquid with a small proportion of vapor. We will be discussing a little bit detailed about the implications of such situation, and so we will continue our discussion on the principles of microthermometry with the help of such simple phase diagrams. Thank you.